Welcome to a new chapter, everyone. We wrapped up content from chapter 8 on Tuesday. And just to give you an idea of how all of this fits together, we are still continuing down this road of hypothesis testing combined with confidence intervals, looking at how those aspects of statistical inference are related to one another. But where we're taking a turn now is in chapter 8, we considered the context of having one sample from one population. And so the belief that we had about the population, or equivalently, the null hypothesis that we formulated, that made a pretty specific statement about the hypothesis. We believed that the mean was equal to, say, 100, or that the population proportion was equal to 0.4. We had some specific value, and we then took the evidence in our sample to assess whether that was a reasonable hypothesis or not. Well, now in chapter 9, we're expanding how we approach the problem by not having a single sample anymore, but by having two different samples. So we're going to today look at the idea of a z-test. Z-test, again, that should be a keyword for telling you underlying normality. But specifically, we are going to look at situations where we have two different populations and we are obtaining a sample from each of these populations. So we want to compare the two populations to one another in some way. But the way that we can do that is by obviously not being able to observe the entire populations. We're going to take a sample from each population, and that is what we will then compare. So the plot that you have up on your screen, this just illustrates different scenarios that are possible. Each of these bell curves represents a normal distribution. And so what I want you to notice here is just the following. The two figures that you have on the left, those two bell curves, they have different mean values. The bell curves on the right, each of those represents a scenario where the means are the same. The top right one, the two normal populations have different variances, but bottom right, they're exactly the same. So the two figures on the left represent normal populations with different means, and the two figures on the right represent normal populations with a common mean. And of course, the variances do different things throughout. So what we'll be focusing on in this chapter is developing tests which can distinguish situations as illustrated on the right from situations as illustrated on the left. So the variances of the underlying populations kind of take a back seat here. They'll still be part of how the calculation is performed, but we want to develop testing procedures for whether two normal populations have a common mean. And we are going to consider two different scenarios in which we can implement a z-test today. So because we have two populations, we need to have two different samples. And we are going to make the following assumptions about these populations. Firstly, we are going to assume that these samples are obtained independently of one another. So we're going to have a sample, say x1 through xm, so m different observations, and each of these is drawn from a normal population with a mean of mu1 and a variance of sigma 1 squared. And then we're going to have a second sample, y1 through yn, so n different observations, and each of these is drawn from a population with a mean of mu2 and a variance of sigma 2 squared. And to keep things simple at first, we are going to assume that the variances sigma 1 squared and sigma 2 squared are known. And what we want to do is develop a way of comparing the two population means to one another. And we're going to do that by looking at the difference of the two means. So we're defining a parameter delta here, and delta is defined as mu1 minus mu2. So it's the mean of the first population minus the mean of the second population. So because we have two samples, we need to calculate some summary statistics from each of them. Now, at the moment, we're assuming that the variances are known, but of course, the population means are unknown. Those are the quantities we want to compare, so that's what we're developing a procedure for. So we take our observed X sample and calculate the sample average for the observed X sample, and then we take our observed Y sample, calculate the average for that quantity, and that ultimately lets us estimate or calculate a point estimate of what the difference is between the two means. So delta hat equal to the mean of the X sample minus the mean of the Y sample, that is our best estimate or our best informed guess based on the evidence that we have collected as to how far the two population means are from one another. So if you were only going to calculate a single number to assess whether the two population means are close or not, you would calculate delta hat. Of course, if you recall, when we were talking first about confidence intervals, a few things came up. The reason we developed confidence intervals was to compensate for some of the deficiencies we have in calculating a simple point estimate. For example, the fact that this delta hat doesn't directly account for how big our sample sizes are in each of the two samples. It also doesn't account for the underlying variability. So we're going to now develop both a method for constructing a confidence interval for this parameter and also develop a hypothesis test for specifically comparing two population means to one another. So that's our goal here. We have a sample from an X population, a sample from a Y population. We call the means of those populations respectively mu1 and mu2, and we want to compare them to one another. So we are interested in what the true value is. Of course, true value here means unobserved because we are unable to do a complete census of our population. So we want to know what the true difference is between the two population means. If we're in a hypothesis testing situation, we're typically going to have some value delta naught, which is the hypothesized mean difference. So if we formulate a null and an alternate hypothesis here, our null hypothesis is going to be that, delta is equal to delta naught. And the alternative can again either be a complete negation or it could be a directional negation, so a partial negation. Now, what you'll see a lot of the time is that it's fairly common that we have this delta naught equal to 0. That's not always going to be the case, but it's a very common situation encountered. Think about that for a moment. What do we know if the true difference is 0? That tells us there's no difference. So often we're going to hypothesize that the two bell curves have the same center or the same average. And in those instances, the null hypothesis will be formulated as delta equal to 0 versus some alternative that negates that. Now, you already know that the section is called a two-sample z-test, so that should suggest to you that the test statistic is again going to be z value. And in this case, z observed is defined as delta hat, so the difference of the sample means, minus delta naught divided by the square root of sigma 1 squared over m plus sigma 2 squared over n. So in the denominator there, that's where we take account of the two underlying population variances. And the distribution that we use as a reference here is our standard normal distribution. So whatever the z observed statistic is, we'll evaluate where that lies on a normal curve. So I'm briefly going to summarize here the formulas for the p-value, but these should look very familiar because they're not going to deviate from how we constructed them in the one sample setting. For example, if your alternative hypothesis is that delta is not equal to delta naught, what that tells you is, if you're imagining a normal bell curve centered at 0, you'll have two tail areas that you want to compute. That defines your p-value. And so the formula for this would be 2 times the normal CDF at the negative of the absolute value of z observed. If you had a one-sided alternative, say delta greater than delta naught, here, if you visualize your bell curve, you only want the area in the upper tail. So this would have a p-value equal to 1 minus the normal CDF at z observed. And finally, if your alternative was one-sided in the other direction, so delta less than delta naught, now you want the area to the left of your observed z value, and this is just going to be the normal CDF at z observed. And if you go and compare these to the one sample situation, once you've calculated z observed, the calculation of the p-value is exactly the way we previously did that. Now, what about the case where we can't assume normality? Well, luck's on our side, perhaps not luck, maybe it's more accurately called the central limit theorem. So central limit theorem is on our side. If both of our sample sizes are large, so if we check if the X sample has at least 30 observations and the Y sample has at least 30 observations, then we don't require normality. In this instance, the z-test can still be used as an approximation. Now, the test statistic is going to depend on whether you're in a situation where you know the population variances or whether you have to use sample estimates. So there's a way to calculate it with known variances and a way to calculate it with unknown variances. For known variances, it's going to look exactly the same as previously. Z observed will be delta hat minus delta naught over the square root of sigma 1 squared over m plus sigma 2 squared over n. If the variances are unknown, however, we have to use sample estimates. So let's just say S1 squared and S2 squared are the sample variances calculated in the usual way. So the way we've always been calculated, we've always calculated them in this class. So in this case, Z observed is just going to be delta hat minus delta naught over square root of sigma 1 squared of, sorry, my bad here, S1 squared over M plus S2 squared over N. But in both instances, your reference distribution is going to be a normal 0, 1, albeit that's an approximation that relies on application of the central limit theorem. So those are the two situations we're considering today. Let's now briefly talk about how we would construct confidence intervals in each of these situations, because we know the conclusions we reach by looking at a confidence interval should not contradict the conclusions we reach when we do a formal hypothesis test, at least not in the case of a z-test or a t-test, because it's the same underlying theory that gives us the hypothesis test and that gives us the confidence interval. So let's consider our two scenarios. Firstly, if we have populations that we know follow normal distributions and the population variances are known, then we can construct an exact confidence interval. And the formula for that is given by delta hat plus or minus z of alpha over 2 times the square root of sigma 1 squared over m plus sigma 2 squared over n. And remember, this is an exact interval. As long as you have populations that are normally distributed and you know the variances, then this formula will give you an exact confidence interval with coverage level 100 times 1 minus alpha %. There are ways of doing one-sided confidence intervals here as well. I'm not going to delve into that in class today, but an example like that may come up in our live Zoom session for this content tomorrow. Now, what about confidence intervals when we do not have normality? So we're in a situation where we don't know that our populations are normal, but the sample sizes M and N are large enough. In this case, we can still use the same underlying structure and we will obtain an approximate confidence interval. So two formulas here, depending on if we know the variances or not. If the variances are known, then your confidence interval is given by delta hat plus or minus z of alpha over 2 times the square root of sigma 1 squared over m plus sigma 2 squared over n. So exactly the same formula as on the previous slide. But if the variances are unknown, we have to replace the sigmas with their sample counterparts. So in this instance, our confidence interval formulas replaces the population variances with sample variances. And just remember, in both of these settings, these are approximate confidence intervals, meaning they don't have exactly the coverage level we're interested in, but as long as the sample sizes are sufficiently large, they're going to be pretty accurate approximations. And we will look at examples of these hypothesis testing procedures, as well as the confidence interval construction during our live Zoom session tomorrow. So I will see you then, and I hope all of you are having a good week.